We'll now cover dynamic longitudinal stability. The information for this topic can be found in chapters 22 and 23 of the book. Recall that static stability was the initial tendency to return to trim after a disturbance. Dynamic stability, on the other hand, is how the airplane responds to the disturbance over time. We can have either a dynamically stable response, a dynamically neutral response, or a dynamically unstable response, to where each subsequent cycle grows further and further from trim and grows without bound. Let's say we look at an aircraft that was in level flight and then had a pitch down disturbance. The three responses here are all statically stable in that they initially are trying to pull the nose up to level flight. But we see we can have, over time, different responses. The darker blue response is dynamically unstable, again growing further and further from trim condition with each oscillation. The light blue response is dynamically damped but still has oscillation. And the red response at the bottom is dynamically overdamped with no oscillation. Again, longitudinal motion is motion about the lateral axis, or the y-body axis, in the plane of symmetry of the aircraft, the XB-ZB plane. And normally longitudinal motion does not couple with lateral directional motions, which greatly simplifies its analysis. In flight test, the principal variables we're going to measure for longitudinal dynamics are pitch attitude theta, angle of attack alpha, airspeed, calibrated airspeed in this case, and elevator deflection. Flight path angle gamma is now defined as the angle between the velocity vector and the horizon. Note that on landing approach, gamma is negative, while angle of attack and pitch attitude can still be positive. Recall the calculus-based technique of modeling aircraft dynamics using stability derivatives and control derivatives. And let's refresh ourselves by walking through these one by one. mu is the change of pitching moment with the change in forward speed. M alpha is the change in pitching moment with change in angle of attack. MQ, change in pitching moment with change in pitch rate. And finally, a control derivative, M delta E, is change in pitching moment with change in elevator deflection. We also talked about these derivatives can be non-dimensionalized by multiplying by things like moment of inertia, true airspeed, wing area, mean aerodynamic chord, and dynamic pressure. And recall that dynamic pressure, Q bar, was defined as 1/2 the density rho times the true airspeed squared. Also, remember that for positive static stability, we required that Cm alpha or M alpha be negative. Recall that we had three longitudinal equations of motion. Let's make some more assumptions. First, that there's constant thrust. So our change in our thrust angle will be 0. Next, we'll assume that pitch rate Q has no effect on the Z force, so those derivatives will go away. The initial pitch angle we can assume to be small, so that our initial theta is about 0, and that the change in pitch rate is equal to the change in theta dot. Also, the change in alpha dot, or rate of angle of attack change, is also equal to the change in theta dot. So when we make these assumptions, the longitudinal equations of motion are simplified and shown in the blue box. Even though these equations are simplified, how do we solve them? They're differential equations, so we can solve them analytically. We can use Laplace transforms, or we can use numerical integration. Let's quickly review differential equations. We're going to focus on first order and second order differential equations. The first order, x dot plus some constant a times x equals a forcing function on the right hand side, f of t. The second order differential equation is of the form x double dot, or two derivatives, plus some constant a times x dot plus another constant b times x equals g of t, another forcing function on the right hand side. When we look at differential equations, we have to figure out what the independent variable is, in this case time, the dependent variable x, what the order is, the second if the highest order derivative is x double dot, whether it's ordinary or partial. In this case it's ordinary, we have one independent variable. Homogeneous, that's whether the right hand side is 0. In this case it's not. We have g of t or f of t as a forcing function. The degree, it's first, the exponent of highest order derivative. And linear, in this case our constants a and b are indeed constant, so it's linear. When we have differential equations, the solution, x of t, has a homogeneous part and a particular part. So we say x of t is the sum of the homogeneous solution plus the particular solution. Let's also review some algebra and trigonometry. We're going to see two functions that pop up a lot when we deal with dynamics of aircraft. One is the exponential function e to the x, and the other is a sine function, sine of omega t. So the exponential function is based on the number e, which is Euler's number, mathematically defined as the sum as n equals 0 to infinity of 1 over n factorial. It's an irrational number, so the decimal places go on and on and on, but I've shown the value of e to 5 decimal places as 2.71828. What's interesting about the e to the x function is the slope of the graph of e to the x at any value of x is equal to the y coordinate, or the value of e to the x. Another interesting function is the area under the curve up to an x value is also e to the x. Now let's look at the sine function. We see that sine waves are periodic, they have a period, and they also have an amplitude. Sometimes sine waves can be shifted by a phase. We often use phi as the variable to denote the phase shift. The amplitude is denoted by a and the period p. We know that frequency is 1 divided by period, when period is time in seconds, and the units are hertz, or cycles per second. But we can also look at frequency in terms of omega, which is 2 pi over the period, and the units are radians per second. Let's go back and look at the first order differential equation. General form, x dot plus a constant a times x equals a forcing function f of t. And we typically, to solve this, we have to have a boundary condition, x at time 0, and we have to know the value of that. But we'll see that there's stable solutions if the constant a is a positive number. And the example on the left shows x dot plus 2, 2 is a positive number, times x equals 10, with the initial condition of x at time 0 equals 0. And we see the plot, x of t versus t. And it's stable. It's not growing without bound. It eventually settles out at some value, in this case 5. On the right hand side, if we make a negative number, in this example negative 2, we see that the function, the y value, grows without bound. So it's an unstable response. Now let's look at a second order differential equation. X double dot plus a constant times x dot plus b a constant times x equals some forcing function g of t. In second order differential equations, we need two boundary conditions. So in this case, x at time 0 is some constant c, and the derivative of x at time 0 is another constant d. We can get a stable solution depending on the coefficients. In this example, x double dot plus 0.6 x dot plus 9x equals 0 shows a stable condition. In other words, it eventually damps out to 0 oscillation. On the right-hand side is an example of an unstable solution. X double dot minus 0.6 times x dot plus 9x equals 0 with some boundary conditions, but we see that this is now an unstable response. With each successive oscillation, it's growing farther and farther from 0 and it goes unstable. We'll now look at solving second-order ordinary linear differential equations of the form a x double dot plus b x dot plus c x equals a forcing function g of t. We know that the solution x of t is the homogeneous solution plus the particular solution. But for now, we're just going to focus on the homogeneous solution x sub h, and we get that by setting the right-hand side g of t equal to 0. We then assume that the solution x of t has the form x equals e to the st, where s is a constant. If we assume that and take one derivative, we get s e to the st. If we take two derivatives, we get s squared e to the st. We'll then substitute those derivatives back into the original equation with the right-hand side equal to 0, and we get a s squared e to the st plus b s e to the st plus c e to the st, and then equals 0 on the right-hand side. We can now factor out e to the st, and we get in the parentheses a s squared plus b s plus c. The only way the product of those can equal 0 is if either e to the st equals 0, and that's not very interesting, or a s squared plus b s plus c equals 0. And we call that equation the characteristic equation. We can relate coefficients in the characteristic equation to damping and frequency parameters. Again, a s squared plus bs plus c equals 0 is the characteristic equation. But we also have the damping and frequency equation of s squared plus 2 zeta omega n s plus omega n squared equals 0. So we can relate the coefficient a to the damping and frequency equation 1. Likewise, b equals 2 times zeta times omega n, and c equals omega n squared. The parameter zeta is called damping, or damping ratio, and it's a measure of the rate of convergence or divergence of an oscillation. Does the amplitude shrink or grow over time? We said earlier that frequency omega is radians per second, but in this case we have a subscript, either a d or an n. The damped frequency, omega sub d, is the frequency we'll observe from a time history. The natural frequency, omega n, is what we would observe if the damping was 0. The plot on the right shows the different damping ratios of zeta from 0.1 to 0.6, and then eventually zeta equals 1, which is critically damped, and then if zeta is above 1, we say that's overdamped. There will be no oscillations if zeta equals 1 or a number greater than 1. We can relate the damping ratio zeta, the natural frequency omega n, and the damped frequency omega d on the complex plane or the S-plane. Again, the frequency and damping equation is s squared plus 2 zeta omega n s plus omega n squared, and we set that equal to 0. To solve that, it's the quadratic formula. S equals minus 2 zeta omega n plus or minus the square root of 2 zeta omega n quantity squared minus 4 omega n squared divided by 2. And we can see that the y coordinate of S, of the solution S, is the damped frequency omega d, and the hypotenuse, or the radius from the origin to that point, S, is the natural frequency. We can also relate the damping ratio zeta to the angle that's made from the vector that goes from the origin to the point and the horizontal axis, theta. And we know that the damping ratio is the cosine of that angle, theta. Let's now see if we can pull out damping and frequency from one of the equations of motion. And the equation of motion we'll look at is our pitch acceleration, or delta theta double dot equation. So we've already assumed that delta alpha dot was the same as delta theta dot. To take another derivative, then that just means delta alpha double dot will equal delta theta double dot. Next, let's just assume that the change in forward speed is approximately 0. Not the forward speed, but the change in forward speed. So with those assumptions, we can then make some substitutions and simplify our equation. Delta theta double dot equals mu delta u plus m alpha delta alpha plus mq delta theta dot plus m delta e times delta e then becomes delta alpha double dot equals m alpha delta alpha plus mq delta alpha dot plus m delta e delta e. Now let's move all the alpha terms to the left-hand side. What we get then is delta alpha double dot minus mq delta alpha dot minus m alpha delta alpha equals m delta e times delta e. So now we have a homogeneous equation, and when we set the right-hand side equal to 0. We see that our homogeneous equation involving delta alpha is in the same form as that standard characteristic equation, which then can be related to the damping and frequency equation. So the value of little a in the characteristic equation is 1, little b is minus mq, and little c is minus m alpha. With that, we can relate the coefficients to the natural frequency omega n and the damping ratio zeta. Omega n, the natural frequency, is going to be the square root of negative m alpha. And we know for stability, for static stability, m alpha needs to be negative, so it's going to be negative and negative, and that will be a positive real root. But we have the equation for natural frequency in terms of the stability derivative m alpha or cm alpha. The damping ratio zeta is minus mq divided by 2 times the square root of negative m alpha. So what this tells us is frequency depends on our longitudinal static stability derivative cm alpha, but that the damping ratio depends on the longitudinal static stability cm alpha and the aerodynamic pitch damping cmq. We talked about another way to solve the differential equations by using Laplace transforms. This is a picture of Pierre-Simon Laplace, and he came up with a very convenient way to solve differential equations. It moves the problem from the time domain to the frequency domain, or the S domain. But what's neat is it transforms a differential equation to an algebraic equation. Some of the prerequisites are we have to have linear differential equation with constant coefficients, time invariant coefficients, and we can use with or without a forcing function. But the definition of the Laplace transform takes our function in time and then changes it little f to a capital F, changes the variable time to the Laplace variable s, but it's just an integral. It's the integral of the function in time times e to the minus st dt, and you integrate from 0 to infinity. The Laplace variable s has a real component and an imaginary component. The real component is sigma, and the imaginary component is omega. J in this case is the square root of -1. When we use Laplace transforms to solve differential equations, if the initial conditions are 0, and that's what we typically start with in trimmed flight, then we'll see that derivatives in time end up being s raised to the power of the derivative. So one derivative, or x dot, is now x times a function x. Two derivatives, x double dot, is now s squared times a function x. And so we can take a time domain second order differential equation like x double dot plus 2 zeta omega n x dot plus omega n squared x equals g of t, and then show what the Laplace transform of that is. In this case, it's s squared x plus 2 zeta omega n s times x plus omega n squared x equals g. And when you go from time domain, functions have lowercase letters like x and g. When you go to Laplace, those letters become capital. Airplanes are in general multi-input, multi-output systems. And the best way to model a multi-input, multi-output system is using a state space model. In the time domain, a state space model has a state vector x, and the derivative of that state vector, x dot, is a matrix A times the state vector plus a matrix B times an input vector u, which can have multiple inputs. We can get the homogeneous solution by simply solving x dot minus ax equals 0, or setting the right-hand side equal to 0, or the forcing function equal to 0. That's a state space model in time domain. In the frequency domain, we just take the Laplace transform and we replace single derivatives with s, and in this case all we have is a single derivative. So our state space model after a Laplace transform is simply s times x, the state vector, which is now a capital, and we replace the time vector with the Laplace variable s, equals the same A matrix times the new state vector x plus B matrix times our input vector u. The homogeneous solution is going to be Si minus A, and I is the identity matrix, times the state vector x. And to solve that, we have a characteristic equation which is the determinant of Si minus A equals 0. We can now take the Laplace transform of all three of the longitudinal equations of motion that have derivatives and are in the time domain, and we can end up with three new longitudinal equations of motion in the S or Laplace domain. Again, single derivatives are replaced with the variable s, double derivatives with s squared, small letters or functions of time become capital, and the time, the variable time, becomes the variable s. We can take now these three longitudinal equations of motion and derive our state space model. Our state vector is going to be forward speed, or change in forward speed, change in angle of attack, and change in theta. Our input, in this case for longitudinal motion, is just the elevator, so we only have one input. But we can rewrite the three longitudinal equations of motion using matrix algebra, and that will give us our A matrix and our B matrix. In this case, our B matrix is a vector. But all we did is take the three longitudinal equations of motion and reformat them based on that definition of the state vector. Next, we'll define what a transfer function is. We want to understand the response of an aircraft to a given control input, so we have to figure out what the associated transfer function is. An example is, how does pitch angle theta change with elevator deflection delta E? We define a transfer function as the ratio of the output to the input of a system. The transfer function is given in a block, and the input is an arrow going into the block, the output is an arrow coming out of the block. But the block itself is the transfer function. And we show some examples. There's a transfer function for delta alpha over delta E, and there's a transfer function for delta theta over delta E. So we've already taken the three longitudinal equations of motion and developed a state space model. State space model was Sx on the left-hand side equals a matrix A times x plus a matrix B times U. And that's shown in the blue. We defined what A matrix was and the B matrix was, and our input in this case is delta E, and our state vector is delta U, delta alpha, delta theta. To get transfer functions from the state space model, we're going to want to bring the AX to the left-hand side and then factor out x. And so we'll have an SI minus A new matrix, times x. We're going to use Cramers Rule, which is from the mathematician Gabriel Cramer, and we're going to have to use determinants. So we're going to review here what a determinant is. But first, if I want to get, I have different states. And for this generic example, we can have a state x or we can have a state y. And to figure out what the transfer function of x, state x is to input f, I use Cramers Rule, which involves the determinant of 1b 0d divided by the determinant of a, b, c, d, and that's shown in the green box. If I want a transfer function of the state y to the input f, then I use the determinant a1 c0 divided by the determinant a, b, c, d. Notice that if the input is f for both transfer functions, the denominator is the same determinant a, b, c, d. In the middle of the chart is just a reminder of how do you get a 2 by 2 determinant. The determinant of ACBD equals AD minus BC. For 3 by 3 determinants, it's a little more complex. Again, consult a math book or go to the internet to figure out and refresh yourself on determinants. We'll now demonstrate how to pull out the transfer function delta theta to delta delta E, or pitch angle to elevator deflection, from our state space model where we have SI minus A on the left-hand side. We use Cramers Rule, which means we substitute the first two columns of the A matrix into the first two columns of the determinant in the numerator, and then the denominator is just the determinant of the A matrix. When you do the determinants, and I encourage you to run through this as an exercise, you'll end up with a transfer function that has a second order polynomial with some A coefficients in the numerator and a fourth order polynomial with some B coefficients in the denominator and a constant K. In this case, K is none other than m delta E. And then the coefficients A1 and A2 are defined below in terms of the stability derivatives and the control derivatives and all the other elements of the matrices A and B, but they're defined here for these coefficients A1 and A2. Likewise, the denominator coefficients B1, B2, B3, and B4 are also defined here. We often show transfer functions with these constants A's and B's, and they're numbers like 6.2 or 7.4, but often students have no idea of where the number 6.2 or 7.4 came from. Well, now you can see these coefficients are based on actual stability and control derivatives and other parameters like true airspeed and theta 0, etc. When we study dynamic longitudinal stability, two primary modes pop out, and they're both come from this fourth order denominator of our transfer functions. And again, it doesn't matter whether the transfer function is delta alpha over delta delta E or delta theta over delta delta E. It's the same denominator, s squared plus b1 s cubed plus b2s squared plus b3s plus b4. This fourth order polynomial can then be factored into two second order polynomials, and both of those can be put into the frequency and damping form, where we can see what the damping ratio is and the natural frequency is. One of the modes has a long period oscillation and a low frequency, and that's called the phugoid mode. The other has a short period oscillation or high frequency, and it's called the short period mode. Let's look at an example. An uncompensated F16. So the fourth order model can be split up into two second order models, or two modes, the phugoid mode and the short period mode. And remember that the coefficients you see in this model come from stability and control derivatives, true airspeed, and other initial conditions. So they're based on real values of the airplane. But we see that the phugoid mode can be factored, the solution, using the quadratic equation, and we see that the value of S is minus 0.013 plus or minus 0.1092 J. We know that the natural frequency of the phugoid mode is 0.11 radians per second, and that the damping ratio is 0.118. The short period mode, again, we can solve using the quadratic formula and know that the values of S are negative 0.95 plus or minus 5.8222 J. The natural frequency is 5.899 radians per second, and the damping ratio is 0.161. We can plot the short period and phugoid modes on the S-plane. The S-plane, again, just shows the x and y coordinates of the solutions of S. One is for the short period mode, the other two are for the phugoid mode. And we're going to plot those with x's. You see that the short period shows up on the S-plane at minus 0.95. For this one, we looked at the positive, plus 5.8222 J. So that's the short period mode on the S-plane. The phugoid, on the other hand, is really close to the origin. But that makes sense, because its x-coordinate is minus 0.01, and its y-coordinate is plus or minus 0.1092. So the phugoid mode, again, is real close to the origin, and the short period is away from the origin on the S-plane. Next, we'll look at the time histories. The phugoid mode, the long period mode, shows that indeed the period of that sine wave is long. It's 35, 45, 60 seconds on average is what a phugoid time period is. And on the other hand, the short period mode on the lower right-hand plot has some dynamic transients, but in about 5 seconds, they all kind of diminish. And so you can kind of see, if you look at the phugoid plot, that the first 5 seconds, you can see the short period there, but then once the short period dies out, the phugoid then dominates the airplane response for the longer term. So let's look at longitudinal modes and understand what's going on. For the phugoid mode, the aircraft remains tangent to the flight path with slow rising and falling, where it exchanges kinetic energy and potential energy. The motion occurs at a constant angle of attack, and we see changes in altitude and we see changes in speed. And again, the period is typically 30 or more seconds. The short period mode, on the other hand, has a rapid transient, and it's dominated by pitch motion of the aircraft. But the speed, on the other hand, is nearly constant. So we get changes in angle of attack, changes in theta, but our speed is nearly constant. And again, the period is short, on the order of 1 to 2 to 3 seconds. Now we'll go into each mode in just a little bit more detail. This is the phugoid mode, and we see altitude versus time on the top plot and airspeed versus time on the bottom plot. We see that the oscillations, again, angle of attack is nearly constant, and we see a trade-off with airspeed and altitude. As altitude goes up, airspeed goes down. As altitude goes down, airspeed goes up. So we have slow oscillation changes in pitch, attitude, altitude, and airspeed, but our angle of attack is nearly constant. And again, we're changing kinetic and potential energy. The pilot typically controls this mode subconsciously, so it's not really an issue for flying qualities of an aircraft. We can get an approximation for the phugoid using our small angle assumption and simplify our model with the characteristic equation of SI minus A, but now A is the matrix for just the phugoid. And we see that an estimate for the natural frequency and damping are shown below. The natural frequency is the square root of negative g times the stability derivative zu over our true airspeed. The damping ratio is negative the stability derivative xu divided by 2 times the natural frequency that we just calculated above. Now we'll look at the short period mode in detail. It involves rapid changes in angle of attack and pitch attitude, theta, and it has nearly constant airspeed, constant altitude, and constant flight path angle, nearly. It's usually the most important longitudinal mode because pilots have difficulty controlling at these frequencies. But luckily for small light aircraft, it's usually heavily damped, so we only have a few oscillations. And the period again is on 1 to 3 seconds, or a frequency of 1 to 6 radians per second. So we can look at the airplane in a classical spring mass damper system, where we have a spring constant, in this case the stability derivative of Cm alpha. Then we have a damping constant, in this case our Cmq derivative. And then we have forcing functions of Cm delta E or Cz delta E. But it's a spring mass damper system that rotates and pivots about the center of gravity. In flight tests, we're going to determine damping ratios and natural frequencies and even pull out what the stability derivatives of Cm alpha and Cmq are. But sometimes it's good to look at the airplane from a design perspective. And the question in this case is, what's the effect if we have a larger horizontal tail? And the effect is it would increase Cmq, resulting in an increased damping and increased natural frequency. And what does that mean on the S-plane? It just means that those values of S, or the poles, are going to start drifting left. So more negative Cmq. Another way in design to increase the effective damping is to actually move the tail further aft. In other words, increase the moment arm. The other way we can change stability derivatives is by moving the CG, or putting, say, a large mass in the nose. What would that do? So if we push the CG forward, it's going to increase Cm alpha. We saw that in longitudinal static stability. So we get a larger value and magnitude of Cm alpha. And so this is going to increase the frequency and decrease the damping, but the primary influence is the increase in frequency. On the S plot, it means that those x's are going to go further up and down in the y-axis. Now we'll look at the FAA's requirements for dynamic stability, and they fall under, at least in the old FAR Part 23, paragraph 181, called dynamic stability. Paragraph A says any short period oscillation, not including the combined lateral directional oscillations, occurring between the stalling speed and the maximum allowable speed appropriate to the configuration of the airplane, must be heavily damped with the primary controls both free and in a fixed position. Paragraph C says if it's determined that the function of a stability augmentation system is needed to meet the flight characteristics requirement of this part, then the primary control requirement of paragraphs A and B, which I left out, of this section are not applicable to the tests needed to verify the acceptance of that system. Again, paragraph B had to deal with lateral directional, and that's why it was left out for this lecture. Paragraph D says during the conditions specified in paragraph 23.175, when the longitudinal control force required to maintain speeds differing from the trim speed by at least plus or minus 15% is suddenly released, the response of the airplane must not exhibit any dangerous characteristics nor be excessive in relation to the magnitude of the control force released. Any long period oscillation of flight path, called phugoid oscillation, that results must not be so unstable as to increase the pilot's workload or otherwise endanger the airplane. So how do we excite the short period mode in flight test? Our input is going to be a doublet. And the doublet can be a square wave or a triangle wave as shown in the diagram. We'll trim the aircraft and then we'll move the control rapidly forward, rapidly back, and back to neutral, and either hold the stick or then release the stick and get the free response. We typically perform these with other stability tests when we're at a trim airspeed, but we want to do it at a variety of airspeeds between our min and our max airspeed, and we sometimes want to vary the frequency of the doublet input, make sure we're at a frequency that is in line with what the aircraft is excited with. The aircraft's control system should include any springs or weights if they are a part of the control system. And again, the reference for the flight test techniques of exciting the short period can be found in the Advisory Circular 23-8C or 25-7A. For data collection and evaluation, an aircraft response after the input should be heavily damped. We know that. Heavily damped is defined as the oscillation being damped within 2 cycles after completion of the input. So we really analyze the response once the input of the doublet is back to neutral. Then we look at the free response and look at overshoots and damping ratios and complete the analysis, again, free response. Next, how do we test for phugoid? We trim the aircraft, and then using elevator alone, we reduce airspeeds 10 to 15 knots, let go, and observe the free response. We'll then want to record airspeed, altitude, and pitch attitude over time. Continuous time if you have a data acquisition system, or every 5 seconds if you're doing it by hand. Once we have a free response output to either the short period or the phugoid, we're going to want to then analyze the damping ratio and natural frequency. So we'll sketch the envelope around the oscillation. We're going to measure various peaks, XO, the amplitude of the oscillation after the forcing function ends and the free response begins, and then other X's, X sub n, the amplitude of the oscillation, some n cycles after our free response has begun. So our amplitude in this case is always going to be a positive number, and then we'll calculate the damping ratio using the equation shown. Let's walk through an example. The top graph is our elevator deflection where our input is into the system. We see it's a triangle doublet that starts at 1 second and finishes at 2 seconds, and then the free response is from 2 seconds on. The bottom plot is pitch attitude theta over time. And we see that after the free response starts, we grab the first peak at about 2.25 seconds, and we note that the amplitude is 1.5 degrees. If I go to the next peak at a little after 3 seconds, I see that the amplitude has diminished to 0.55 degrees. And if I go further to about 3.75 seconds, I see that the amplitude further diminished to 0.2 degrees. So I'm going to record the x0 amplitude, the x1 amplitude, the x2 amplitude. We also can measure the frequency, or the period to get the frequency is the time it takes to go from one peak to the second. So to go from the x0 peak to the x1 peak is 0.75 seconds. I then take the values, the different amplitudes at 0 and some value n, which can be 1 or 2 in this case, and we use the equations for delta. In this case, delta is not elevator deflection, it's just a variable. And then we use that value from that equation, plug it into the equation for damping ratio, the second equation, and get our damping ratio. So if I use n equals 1, Then I grab the data from x0 and x1 and I substitute it in the equation. I calculate a delta value of 1.0033. Plug that into the damping ratio equation and I get 0.158. If I choose to use the data at the second peak, I can do that and use the same equation. It just means that n equals 2 now. So I grab the data from x0 and x2, plug it in the equation. My delta is 1.0075, and I plug that in the equation for damping ratio, and I get basically the same thing, 0.158. An alternate method for determining damping ratio is to use the half-cycle plot. In this case, I would pull off a positive amplitude and then grab the next amplitude on the low side of the sine wave as my half-cycle amplitude. So for this example, our amplitude at the 0 point, again, was 1.5. And if you go back and look at our free response, the amplitude at the half cycle was 0.9. So I ratio these two, 1.5 divided by 0.9, and I get 1.66. Then I enter this plot at 1.66, and note it's on a log scale on the x-axis. So, but between 1.0 and 2.0, I have to eyeball where 1.66 is. Once I enter the plot on the x-axis, I go up, intersect the curve, and then read off the y-coordinate. That's the damping ratio. So in this case, we get about 0.16, which is pretty darn close to the 0.158 we did calculating using the other method. So next we want to calculate natural frequency and damped frequency. And just again to review on the complex plane, the damped frequency is our y-axis coordinate, and our natural frequency is the hypotenuse or the radial distance from the origin to our point. We can relate those two, the damped frequency to the natural frequency, using the equation omega d equals omega n times the square root of 1 minus the damping ratio squared. Again, the damped frequency is what we observe, so that's going to be 2 pi over the period we measured. And we measured 0.75 seconds was our peak-to-peak value of the period. So our damped frequency is 8.38 radians per second for this problem. To get natural frequency, we use that equation, but now solve for natural frequency, and that's omega d divided by the square root of 1 minus the damping ratio squared. Again, we calculated omega d to be 8.38. We divide by the square root of 1 minus our damping ratio, in this case 0.158, and square that, and we see that the natural frequency is 8.49 radians per second. And looking back at the S-plane triangle, we know that the hypotenuse is always going to be greater than any of the legs, so we know that natural frequency will always be greater than or equal to damped frequency. If you're just trying to get a quick damping ratio, the test pilot rule of thumb is, after the input is out, calculate the free response, just count the number of overshoots, and you can estimate the damping ratio using the equation 7 minus the number of overshoots and divide by 10. In this example, we can see that we have 6 overshoots, so 7 minus 6 divided by 10 would give us a damping ratio of 0.1.